Well, hey there, Algebra. Here's our do now for today. Go ahead and figure out how many graph walkers there are in the illustration, and you can hit pause on this video until you have your answer figured out. Well, hopefully you got a chance to get an answer for how many graph walkers there were. I counted 1 here, plus 3 in the next group, plus 8, plus 1 more for a total of 13. And I just, below the picture, rewrote that just with numbers instead of pictures. So I got 1, and then instead of like the little blue stick person, it kind of looks like a little X. So I just used that X as kind of the shape of the graph walker. So 1 of the little graph walkers plus 3 more of little graph walkers plus 8 of little graph walkers plus 1 of little graph walkers gives me a total of 13 little graph walkers. Cool. Today we're going to look at simplifying expressions by combining like terms, and that is our learning target, to be able to simplify expressions by combining like terms. So some vocabulary to start us off here. Algebra expressions or number sentences often contain different types of terms. The way we recognize a term is in that number sentence, it's going to be anything separated by a plus or a minus sign. So an example down here, I've highlighted those different terms, each one in a different color. They're all separated by plus signs. So we can think of those variables like labels. So anything that in this case has an X on it means I'm counting how many X's there are, right? That's the label. Here's the kind of thing I am talking about. And then each of those terms also has a coefficient. The coefficient is the number that is right in front of that letter. And that's telling you, basically, it's keeping count of how many of them there are. So each of the variables in these terms has a count on it, which the vocabulary word is coefficient. And in an expression, if there are terms that have the same variable on them, we can combine those. We'll just group them together and add up to get the total, just like we saw in the do now. We have a whole bunch of graph walkers. We don't need to keep this group separate from this group, separate from this group. They're all graph walkers. Just add them all up and let's find the total. Okay, so in this expression, I've got these different terms. Each of those is a different color. Each of those terms has a coefficient. If there is not a visible number, like on the yellow X there at the beginning, that means a coefficient of 1. It's just like, in normal language, if I have like 1 pen, I don't have to say 1 pen. I can just say I have a pen. And if I don't tell you a specific number, then we know it means 1. That's assumed, right? So the same is true in, this is a rare thing, but the same thing is true in math that is true in normal speech. Pen. It means 1. If I have a different number of pens, I'm going to say 2 pens. So if I'm looking at the coefficients, I have 1 from the yellow one. I got 3 from the green term, 8 X's in the blue one, and then 1 more X in the magenta. So I'm just going to add those coefficients together. 1 plus 3 more plus 8 more plus 1 more. So to find the total of those coefficients. And let's scroll down here. I've got this written out. So the grand total is 13x. So the x is just the label from each of those terms. The label doesn't change, right? There's not a plural form of x in math. So there's the difference between normal speech and math. If I've got 3 pens, I put an S at the end of the word. In normal speech. In math, it's just an X here, 3 X's there, 8 X's there. When I combine them, it's still X, right? So 13X is my total. I don't have to put an S at the end or something. But what people do try to do often is somehow change that to a different letter to make it, like X, and then you'll see, but there's 4 of them there, right? And so somehow I got to get that 4 in there, which it makes sense, but that's not the way this works. Okay, so similarly, here's a problem that a lot of times people will say, oh, there's 7y, take away the y. Oh, well, that means that I'll just take the y off of there, and so I have 7 now. right? Totally makes sense. Also, not the way this works. So what this expression means is I had 7 y's to start with. I took away 1 of them. So really this means 7y minus 1 of those y's. You could imagine like the y's represent pens or chairs or pieces of candy, whatever you want. I had 7 of them. I took 1 of them away. So now I have 6 y's, right? If it's 7 pieces of candy and I take 1 of the pieces of candy away and give it to my friend, I still have 6 candies, right? So that Y is like the label, like whether you call it pieces of candy or pens or chairs or the letter Y, the label doesn't change. We can add or subtract those coefficients. The label always remains the same. Okay, here's another one. Z minus 8Z plus 12Z. So what I need to pay attention to are those coefficients. If it helps, write in that invisible 1 so you can see it. And then this is basically the same thing that we did earlier with adding and subtracting integers. Although technically they're not integers because they have a variable on them, but we can treat this exactly the same. So what I'm doing to find my answer is just that 1 minus the 8 plus the 12 to get the coefficient answer. And then I know that that label Z is going to go on there as part of my answer because that is the thing that I'm actually counting. How many Z's are there? So 1 minus 8 is negative 7, and then plus 12 is going to give me positive 5. The label does not change, so this is going to be 5Z.